Okay, this will be the lesson video for chapter 6. This is another multi-day lesson, so we're just going to recover it all at once, but this is actually taught in class over multiple days. Chapter 6 is the last of the chapters in Unit 1, which is being focused on how to analyze data from a single sample with one variable. In Unit 2, we're going to switch to if we have data sets where for each data point we have 2 values, but for now we're focusing on 1. We've covered most of the basics. The only thing is that there's one particular type of distribution of numerical data that just occurs so frequently that it deserves its own chapter, and that is the normal model, right? The normal distribution. So much of statistics later in the course is based on assuming that the data is normal, because we can do so many more things with a normal distribution. We have a lot more tools that we have at our disposal compared to just general distribution. So we're going to focus on that in this chapter 6. First of all, I want to introduce an idea called z-score, and this is a particularly useful thing if you have to compare something from 2 different distributions. Now, this first thing, we don't have to have a normal distribution. This works on any distribution. Let's say we had scores for college-bound students, and some of them took the SAT and some of them took the ACT. And we know that most that if you look at all the scores, worldwide on the SAT and ACT, that they're unimodal and symmetrical, roughly mound-shaped, and they have the following means and standard deviations. So on the SAT, at least the version that back when this was created, the mean score was 1500 with a standard deviation of 250, and for the ACT, the mean score was 20.8 with a standard deviation of 4.8. So let's say that you're part of an admissions decision panel for a college, a pretty exclusive college, and you have 2 students that apply, and they're equal in all other ways, but you're going to have to use their SAT and ACT score to try to decide which one to admit. So one of them happened to take the SAT, and they scored 20/30, and the other one took the ACT, and they scored 30. Okay, so 32, sorry. So how would you compare these two? Because they're different tests. Well, it turns out that we can do that because we can kind of standardize how far above average these tests are, right? Both these tests are above the average. And we can use the standard deviation to figure out how many standard deviations they are above the mean, right? That would actually be very easy to do. And when we do that, that's called calculating a z-score. So a z-score is just a measure of the number of standard deviations, I'm going to often abbreviate that SD, above or below the mean. Okay? Right, and the way we would calculate that is we would just take x, which this represents the data value. We'll subtract the mean to get the distance away from the mean. So if this is a positive number, it means the data is above the mean. If it's a negative number, it's below the mean. And then we divide by the standard deviation to figure out how many standard deviations we are above or below the mean. And because this division divides out the units, the z-score has no units. And that means we can use it to compare results from different data sets. Okay, so let's go back and look at that particular example that we just had, and then I'm going to, let's say we wanted to compare these two. So student 1, we could calculate a z-score for the SAT student, right? That would be that they scored 20/30 when the mean score was 1500, and then we know that a standard deviation is 250, right? So if you took 20/30 minus 1500, that means that they were 530 points above the average, right? But since a standard deviation is 250, that means that they were 2.12 standard deviations above the mean, right? So that's fairly unusual. Remember we said in earlier chapters that something that was more than 2 standard deviations is definitely considered like in the outlier range. Okay, but let's look at this student, the ACT student. Right, they scored a 32, and the average on SAT is 20.8, and the standard deviation is 4.8. So this student was 32 minus 20.8, which is 11.2 points above average, right? But a standard deviation is 4.8, so 11.2 divided by 4.8 for each standard deviation means this student is 2.33 standard deviations above the mean. Right, so while both of these students are better than average, and in fact way better than average, almost to the point where we would consider them, well, we would consider them outliers, this student is further above the average than the SAT student. So if we were just using this criteria, we would admit the ACT student because they're further above the average. And the z-score, by comparing standard deviations, that gives us a standardized way to compare, even though we have two different units, right? And that's the reason why it's called the standard deviation, because it's standardizing the deviations. All right. So at this point in the class, we would normally require people to go ahead and take the Chapter 6 required practice packet and just go ahead and work the first problem. And so let me take a quick look at that. So I just want to see if there's anything I want to make a comment on before we move on. Yeah, so I'll let you just do that. That is a problem exactly like the one we just did. So you should be able to do that. Check answers in Schoology. The solution should be posted by now in the materials section. You can see if you're getting these right. Okay. Next thing we want to talk about is how many standard deviations away from the mean does a data value have to be considered significantly different from the mean? Yeah, and we said in general, right, maybe 2 standard deviations, but we didn't really justify that. So one way to answer this would be if we had a way to model the distributions of data values, right? We know that many data sets are normal and symmetrical and have this kind of mound shape, right? In fact, this particular shape that's represented by this blue curve occurs so frequently in nature. Anytime there's anything which is kind of natural, like if you measure the weight distribution of elephants or the lengths of human male forearms or, you know, anything natural, very, very frequently the things are normally distributed. In other words, there's a common value in the middle, and then there are some above and some below, but that falls off symmetrically and with this general shape. So much so that we call this the normal distribution model. Now, you don't really need to know this, but for those of you that have calculus courses or brief calculus, this would be the probability distribution function for that. And it turns out that you can type in any particular data value, and then this would tell you how likely it is for a data value to be in that range. The only thing that's interesting about this weird and crazy formula is that there are 2 parameters, just like we have, you know, y. If we have a line, we have y equals mx plus b. You know, we have these 2 parameters, the y-intercept and the slope, that we can vary. And just selecting those 2 parameters, we can specify any line we want. Well, in this normal distribution, we have 2 parameters as well. One is the standard deviation, and one of them is the mean. Okay, now I'm using a little bit different symbols than we've used before, but we'll go ahead and talk about that. But I want to show you something, so I'm going to switch here to an online app to demonstrate something. Okay, so hopefully you should be able to see this app. This shows this blue curve is a normal distribution, and then what I have are sliders here that allow me to change the mean. And if I change the mean around, notice what happens is that the center of that mound shape moves back and forth. But when I do that, the standard deviation is unaffected, right? On the other hand, I can position this somewhere on a mean, and then if I change the standard deviation parameter, then if I make it smaller, then there's more data closer to that mean, and if I make it larger, there's more data far away, right? But that also does not change the mean. So these 2 things can be varied independently, and that's nice because that means that if you have any set of data, you can just select the mean to be right at the center and adjust the standard deviation for your model until you roughly match the data. So we can create a mathematical model, like a perfect normal distribution, to approximately model any normally shaped data. Okay, so let me switch back to the presentation again, and we'll take a closer look at what we can do with normal distributions. Okay. So, so we know we can vary these parameters, and we can make this sit on top of any distribution that's roughly mound-shaped and model it, right? So let's comment a little bit about some of the different notations that we saw there. So one thing is, we'll talk about this a lot more formally later in the class, but even now I want to start talking about it. When we're studying something, we're usually studying something that we call a population. Like, for example, maybe we want to study all of the adults in the United States of America, right? That would be the population. but we very, very rarely have data on the entire population, right? If we do, it has a special name. It's called a census. But usually, instead of having a census of the entire population, we actually just have a sample that we took from that population. So we have a representative sample, right? And we're usually working with the sample and analyzing the sample. And that's what this whole first semester is about. It's about how do you analyze the sample, right? And then in the second semester of this class, we're going to talk about how can you take what you learned about the sample and infer things about the population that it came from. So that's the subject of the second semester. But right now I want to make a distinction. If we're talking about the population, we usually use Greek letters when we're talking about anything to do with that. And when we're talking about a sample, we usually use English letters for the sample, right? So when we're talking about a population, right, the things that we're going to measure about it, like say the mean and the standard deviation, those things are called parameters. So P for parameters goes with P for populations, right? But when we measure those same things for the sample, then they're called statistics. S for statistics goes with S for samples. And to keep them straight, we have different letters or symbols that we use, right? So we've been using X bar for the mean, and we've been using S for the standard deviation because we're talking about samples, right? If we're talking about a population or a perfect model that's supposed to model a population that a sample came from, then we switch to Greek letters for the population. And we use this letter here, which is called mu. It's the lowercase m in the Greek alphabet. And we use this letter, which is sigma, lowercase s in the Greek alphabet, when we're talking about standard deviation. So we either use X bar for mean if we're talking about a sample, we switch to mu for the mean if we're talking about a population or a model, and then S for standard deviation for data, for samples, sigma for standard deviation for models. And that's the reason why when I wrote this formula out, I used the Greek letters, because this is a perfect model, like a perfect model of the population that this came from. So you could have, for example, a population that has a mean and a standard deviation, and when you take the sample from it, you're going to have a sample mean and a sample standard deviation, but they're not going to exactly match up with the population. And one more thing that I can note for you, and that is that when we're talking about specifically a shape of population or sample which is normal, we can sometimes use this shorthand. A capital N stands for normal, and then we can put in parentheses whatever its mean and standard deviation are, right? Okay, so I'll use that notation as we go throughout here. Okay, so just to kind of talk a little bit further about this, right? Since we're taking a sample and it's representing the population, it means that this sample mean is an estimate for the population mean that it came from. And this sample standard deviation is an estimate of the standard deviation of the population. So the statistics are basically estimations of the population parameters. Okay? All right, so every time you work with a problem that involves a normal distribution, you should sketch the distribution. That's actually a requirement in this class. And then mark the mean and standard deviation like this. So let's say, for example, that we had a distribution of test scores and we knew that the mean, so maybe this is a sample, so I'll say X bar, the mean is 75, and then the standard deviation was 10 on that, okay? So if I knew this was normally distributed, I could sketch a normal, which just looks like a mound like this. And then we know that for normal distributions, everything is symmetrical. So the mean would be right at the center, 75, right? So how wide do you have to label this? Well, it turns out there's a trick. Okay, if you have a normal distribution and you go about 61% of the way up, right, then, and you draw a line across this like that, then this distance right here for a normal distribution turns out to be the standard deviation. And also on this side, because remember, the standard deviation is the average distance from the mean that the data is, and that means both above and below the mean. So if this was 10 and this was 10, then we would say that down here, if this was 75, if I want one standard deviation higher than that, that would be where 85 is, the score 85, and 75 minus 10 would be where 65 is. So anytime we do anything with normal distributions, I'm going to require you to make a sketch, label and what the mean is, and then draw the line across here and label the standard deviation in here, and then also write in what is the value that's one standard deviation above the mean and one standard deviation below the mean. Okay? All right. The other thing about this, if you've ever taken a calculus class or brief calculus, is there is a special definition of these points. These points, if you recall from calculus, are when the second derivative changes sign. So this curve is curving in an upward way over here. So the second derivative would be positive, concave up. And then right here, this switches to curving in a downward way, so that the curvature is negative. Right at that point where it switches from curving up to curving down, remember in calculus, if you've taken a calculus class, this is called the inflection point. And so this line happens to also be from the inflection point to the inflection point, right? But for most of us, you can just remember, go a little way more than halfway and draw it, and you'll be good, okay? All right, so when we represent data, right, we can use the actual data values, like say a test that has an average score of 85 with standard deviation of 7 would look like that, right? Or if we wanted to, we could instead take every single test score and figure out what its z-score is, how many standard deviations above or below the mean we would be. So for example, if I wanted to take this test score that's at 92, I could put it through that z-score formula. 92, the data value, minus the mean of 85, is this score is 7 points higher than the average of 85. And then if I divided that by the standard deviation 7, we would be exactly 1 standard deviation above the mean, right? So this data value, which is right at the end of this line right here, right, is also 1 standard deviation above the mean. And if I did that calculation with the score right at the mean, this would be 85 minus 85 over 7, which would be 0 over 7, which is 0. So that means that a data value that's right on the mean has a z-score of 0, and a data value that's 1 standard deviation above the mean has a z-score of 1. So you can actually make a plot of the data, a normal distribution, but instead use the z-scores of the data instead of the original data. Okay, so if you have the original data, you would be centered at the actual mean, right? But if you have a z-scores, this would always be centered at 0, right? Because the middle point is always 0 distance from the mean. And then at the other end of these lines, this point over here would be +1, and the point over here will be -1, right? So if you make a sketch of a normal curve for z-scores, you'll always have a 0 in the middle, and when you draw your line, this value here, this will be 1 and 1, so this will always be 1, and this value will always be -1, okay? So we go back and forth between these two things depending on what we're trying to do. Sometimes we'll use the data, and sometimes we'll use the standardized data, which means to use the z-score. So in this case, we're doing a normal distribution with an actual specified mean and standard deviation. And for z-scores, we always have a mean of 0 and a standard deviation of 1. We'll see later why that's important and how it will be used. Okay, at this point, we would normally have you go and on the second page, go ahead and complete problem number 4. So you should pause the video, try that, and then check answers. Okay, so next thing we'll talk about is the fact that the normal distribution model is really a probability density function. That means that if you were to sum all the area under this curve, it's like adding up the total counts, and therefore it has to add up to 100% of the data, or a probability of 100%, okay? And that means that if we ever want to know what percentage of the data is in a certain region, we can just figure out what percentage of the area under this normal shape is in that region. Okay, so we would say that I could define, say, a lower boundary of some region and an upper boundary, and then kind of shade that area in there. And then that's going to be some percentage of the total area. And so whatever that percentage is, we can also think of that as being the probability, because that means if you had a set of data and you took one piece of data from that, the probability that it would be in this shaded area would be the same as the percentage, okay? And there's a function in our calculator called normalcdf that everyone should have seen at some point in the past that allows us to find the percentage area or the probability of being in a certain region of a normal distribution. And so what we have to do is we have to give that function the lower bound and the upper bound of the region we're interested in, and then we also have to specify what the mean and standard deviation is, okay? Okay, so there's one function that is if you have the boundaries, so you know what area you know what the boundaries are, and we need to know what percent area that is. To go from the boundaries to the area, you use normalcdf. And there's another calculator function called invNorm that does the reverse, right? If you know the area, but you want to know what the upper boundary is of that area, you can use inverse norm and specify the area to the left along with the mean and standard deviation, and it will tell you what the boundary is on that scale. Okay, so you use normal CDF when you need the area, and you use inverse norm when you need the boundary. Okay, so most of this, if you're just listening to this, probably pretty confusing, but when we look at some examples, I think this will make it a little clearer. So let's take a look at some examples here, and I'll show you what is meant. Okay, so let's say that the scores on tests are normally distributed with a mean of 85 and a standard deviation of 7. Okay, all right. So if I wanted to answer this question, what percentage of the scores are between 70 and 86? The first thing I would do, and you're required to do this every time when in this class, is make a sketch of the normal distribution. They told me it's normally distributed. They told me the mean is 85, so I'd put that there. They told me the standard deviation is 7, so I'd draw my line and say this is 7 and this is 7. And so 85 plus 7 turns out to be 92, right? So this will be 92 out here. And if I go one less, that's going to be 78, okay? And then I want to know what percentage of the scores are between 70 and 86. So I'm going to switch colors here. But if this is 78, 70 is way out here somewhere. And 86 is just a little bit above the middle like that. And so I'm trying to find what percentage of the area is in that area right there, right? All right, so now we would resort to our calculator. So I'm going to switch now to sharing the whole screen so we can see all of this together. And I'll bring up a calculator, and we'll go ahead and find that using the normal CDF function. So what I'm going to do is use a function called normal CDF. Okay. And so it's going to be normal CDF from, let's see, actually, let me make this a little bit, I'm going to write it down here on the bottom because this is getting too small. And then we'll use other screens for the other ones. Okay, the first thing we have to do is we have to specify the lower boundary and the upper boundary of the region that we need shaded. So that's going to be these red numbers, 70 and 86. In fact, I probably should have done that in red. Let me just do that in red, right? These numbers come from the boundaries that we're trying to use, right? And then we have to know, well, what is the mean and standard deviation? So this is a mean of 85 in the middle. We should label that the mean. And then the standard deviation is 7. That's the standard deviation, right? So whenever we do a calculation like this, you're required to do a shaded sketch of a normal distribution and also the calculator statement with everything labeled. That's because this is what AP Statistics exam requires for full credit. And we just want to get in the habit of it. So by the time you get to that test, you're just doing it, second nature. So here's how you do this on a TI 84 or 83. See where it says DISTR above the variables key? We're going to hit the color key and then the variables button to get the list of distributions. And the second one down is normal CDF. Okay, so we'll select that. And then if you have a TI 83, it'll just say that it'll say this, and you'll have to know to type these numbers in this order with commas in between, the commas above the 7. If you have a newer one, it'll prompt you. So we would enter 70 here and then hit the enter key, right? And then 86 for the upper boundary, and then 85 for the mean, and then 7 for the standard deviation. And note that they use the symbol mu and sigma in the calculator for the mean and standard deviation. Okay, so we just have to know that's what that means, and then we just go ahead and hit enter. It'll paste it into the function, and then we hit go. And this will give me a value between 0 and 100%, except expressed as a decimal. So it will be 0.5. I like to use 4 decimal places. The official rule is anything reasonable, but I would say go at least 3. And what this is basically saying is around 54.07% of the test scores are between 70 and 86. Okay? All right. So then let's take a look at the next problem. And for that one, I'm going to copy this screen so that we have some workspace. But for this one, we will now do part B. Okay, so for part B, it says what percentage of scores are between 78 and 92? All right, so to do part B here, I would start by doing a sketch. And the sketch will be, we have the mean in the middle at 85, have the standard deviation 7 on each side. So this is 92 and this is 78, okay? And so I'm going to switch colors here to do the boundaries. The boundaries are 78 and 92, okay? So we're shading that. So really we're finding out how much data is between one standard deviation below and one standard deviation above. So we'll do our calculator statement, and that is that it's going to be normal CDF from 78 to 92 if the mean is 85 and the standard deviation is 7. And we're required in AP statistics to label these values: lower, upper, mean, and SD for standard deviation. And then we would use the calculator to actually get us the value. A little faster here. So from 78 to 92, if the mean is 85 and the standard deviation is 7, gives me 68. So 68.27%. So for any normal distribution, about 68% of the data is within one standard deviation of the mean. Okay. All right. Let's do another clone of this page so we can do the next problem. Okay, so for this one, we'll start over. But this time, let's go ahead and do problem number C. Same thing, we're going to do a score, but this time it says what percentage of scores are between z equals -1 and z equals 1. So they're telling me standard deviations. And that means whenever we do z-scores, we switch when we do our sketch to using the standardized z-score version. Since I have z-scores here, right, that means this is always 0 and this is always 1. So this is +1 over here, -1 over here. And so the boundaries they're asking us to compute this time are from z is -1 to z is +1. And that's also the same thing. So I'm expecting this to be 68% again. But let's go through the whole process of what you'd have to show on a quiz or a test. Normal CDF. This time we would say the lower boundary is -1 and the upper boundary is 1, but the mean will be 0 and the standard deviation will be 1. So our lower value is -1, our upper value is 1, our mean is 0, and our standard deviation is 1. And if we do that in a calculator, normal CDF from -1 to 1 z-score, and for z-scores the mean is always 0 and the standard deviation is always 1, then we get that same 68.27%. Okay, so we can do the same process whether we're working with the original data or whether we're working with z-scores. The only thing is for z-scores, we always use 0 and 1 for mean and standard deviation. Okay, let's do the next one. So for the next one, we are going to do problem D. And for problem D, it says what percentage of scores are below the z-score of -1.5? Okay, so we'll draw a sketch. Okay, this is z-scores, so I'm going to use 0 and 1. This is 1, this is -1. And this just says below -1.5, so they only gave me one boundary here. So if I went to -1.5, that would be about here, -1.5, and it just says below that. So there's no lower boundary, right? So where is the lower boundary? Well, it turns out that the normal distribution goes on forever in both directions. So the lower boundary is actually -infinity, okay? It goes all the way to -infinity, even though this is a test and you probably have a minimum score of 0. Because we're using this model, we actually need to use -infinity as the lower boundary. Okay, and so what we'll do when we enter this in a calculator is we would say normal CDF. We have to have something to enter for -infinity. So we just say negative and then a really big number like -9999 or something like that. And then we have -1.5 is the upper boundary, with 0 is the mean and 1 is the standard deviation. So again, label this lower, upper, mean, standard deviation every time. Just get used to doing it every time. That way you'll get it right on every test. And you'll also get it right if you take the AP statistics exam. So we'd put in something like -9999 for the lower boundary, -1.5. Remember, whenever you're ending your negative numbers, you have to use this negative, not the subtraction key, or you'll get an error, 0 and 1. And so that is 0.0668, which is about 6.68%. Okay. And the nice thing about the sketch is it gives me a sanity check, right? This is a very small percentage, and sure enough, that would be a small percentage. If I go back, right, this should have been pretty large, so it's not surprising to me that came out to be 68. Okay, and then let's do this last one on this page. All right, so for this one, it asks us to say what score would you need to get on this test to be in the top 10%. And it suggests that we work it both ways, using Z and using X. I think let's just use the Z score. I'll show you one way to do it. A good way to do it is, well, there's two ways to do it. Let's use the data first. So for the data way, what we could do is we could say, all right, the data is centered at 85 with a standard deviation of 7, right? So this is 92 and this is 78 plus or minus 1 standard deviation. And if I just roughly draw a line where the top 1% would be, it would be way out here, right? Where this area here is 0.01, 1%. That's 0.01 is 1% in decimal. And our job is to figure out this boundary value. Now, so far all these other ones, we were finding a percentage, which was the area. This is the reverse. So now I'm going to have to do this with the other calculator function. So the other calculator function is inverse norm. Inverse norm, and what you have to do is enter the area to the left along with the mean and standard deviation. Okay, so the mean and standard deviation here would be 85 and 7, but the area to the left, okay, so if the area to the right of this boundary is 1%, the area to the left would be the other 99%. So I'm going to enter 0.99, the area, as a percentage, but expressed as a decimal. Okay, and when I do that, this is found in the same location, but it's the third option down, inverse norm. It's going to prompt you for area. If you have an older TI-84 like I do, you have to enter left area. Some of the newer versions, they allow you to enter an area, but then specify its area, if it's area to the left or the center or the right. And so you could enter 1% and select right, but if you have this kind or a TI-83, you would enter the 0.99 area, and it has to be as a decimal, 0.99. And then I would set the mean to 85. And then the standard deviation to 7, okay? And then what that's going to give me is 101.28. And what that means is our test score would have to be 101.28 to be the lowest score that would get me in the top 1% of this data if it was normally distributed, okay? So that's definitely the way I would work the problem, okay? But there is another way to do it. So let me make a clone of this page again, and we'll do it one more way, just to kind of show you how flexible these functions are, okay? So what I could do is say, let's use z-scores. So if I was going to use z-scores, then I could say, all right, whenever I'm using z-scores, I use 0 as the mean and 1 as the standard deviation. So this is 1 and -1. Top 1% would be up here somewhere, area is 0.01, and I need this boundary. And if I used inverse norm with the z-scores, so I have inverse norm, area to the left is that 99%, but with 0 and 1, so this is left area, mean and standard deviation. So if I do that in the calculator and I use inverse norm, 99% to the left, but I switch to the z-score, 0 and 1 for the mean and standard deviation, then I'm going to get a z-score out as a result. So I'm going to get 2.326. So this boundary would be, we have to be 2.326 standard deviations above the mean. But that doesn't actually tell me a score. So then I'd have another step that I would have to do, which would be to use the z-score formula, which is z is a data value minus the mean over the standard deviation. to convert that. So if I know that the z-score has to be 2.326, and I would like to have the mean, or the data value for that, and I know the mean was 85, and I know that the standard deviation was 7, I could take this equation and solve it for x. Like I could multiply both sides by 7, and then I would have 2.326 times 7, so I would have 16.282 equals x minus 85. And then if I added 85 to both sides, I would get that the data value for the test is 101.28. Right? So you can use these inverse norm and normal CDF functions quite flexibly. All right. All right, let's see. So if you were to use this same idea to figure out what percentage of the data is within one standard deviation of the mean, that would require, I'm just going to kind of do an abbreviated thing here. You would use the normal CDF. And you could say go from one standard deviation below to one standard deviation above if the mean was 0 and the standard deviation was 1. And if you do that, you're going to get that this is about 68%, right? In fact, if I run it real quick, let me just show it being done over here. Okay, so if I went from one standard deviation below to one standard deviation above on a z-score distribution, that would be 0.6827, 68% approximately. If we wanted to be within 2 standard deviations, then I could go from negative z-score of -2 to z-score of 2. And if I did that, from -2 to 2, we're going to get roughly 95% of the distribution, 9544. And if I did the same to within 3 standard deviations of the mean, so from -3 to 3, these standard deviations above and below the mean, we're going to get almost all of the data. So -3 to 3 would give me 0.9973, right? So about 68% of the data is always within one standard deviation of the mean in a normal distribution. About 95% is within 2 standard deviations, and about 99.7% of the data is within 3 standard deviations. And that particular set of facts is sometimes called the empirical rule, right? And it's a good idea to memorize this, that 68% of the data is within 1 standard deviation, 95% is within 2 standard deviations, and 99.7% is within 3. And everything's symmetrical. So like, for example, this middle 68%, 34% of it is over here and 34% is over here. So we can ask what percentage of the data would be above 2 standard deviations, for example. Okay, well, if you looked at all the percentages here, right, that would be 2.35%. And that means that if you're more than 2 standard deviations away in either direction, you're in the top or bottom 2.5% basically, right? So that's definitely unusual. And that's the reason why we sort of can say that anything outside of 2 standard deviations away from the mean is considered unusual or an outlier. Okay? All right. Yeah, so we still haven't answered the question, how many standard deviations leeway from the mean does a data value have to be considered significantly different? Now we just have. If you're at least 2 standard deviations away, you're in the top and bottom 2.5%. Since there's 99.7% of the data within 3 standard deviations, if you're 3 standard deviations away, you're actually in the top 0.15% or the bottom 0.15. So most people say, you know, either 2 or 3 standard deviations. Usually starting at 2, we start to think of things as being outliers or unusual. Okay? All right. Yeah, so if you wanted to go a little bit further, we could look at the box and whisker plot for our IQR definitions, right? We know the upper fence is Q3 plus 1.5 IQRs. And it turns out if you carefully go through that on a normal curve, you'll calculate, and you can pause the video and look at this if you want. This isn't super important, but that happens at 2.7 standard deviations away. So our upper and lower fences for our median IQR way to establish outliers, they actually are between 2 and 3 standard deviations away. Okay. All right, so for normal distributions, you can say if you're plus or minus 2 standard deviations away from the mean, that means that you can consider something an outlier if you're further away than that. Or you can use the IQR rules that are like Q3 plus 1.5 IQR, or Q1 minus, so greater than that, or less than Q1 minus 1.5 IQR. Right, and in general, even if you don't have a normal distribution, this is the general rule we usually use. So it's safe to use those rules that we established at first in the earlier chapters. That's the safest way to say if something is an outlier. Okay, I think, let's see, how much is left in here? Yeah, let's go ahead and stop there for this video. I'm going to break the rest of this into a second part 2 video. So this will just conclude part 1 of the chapter 6 notes.